Welcome back. Now we have a feeling on the quantity of energy. But how do we store energy? To explain this, we have to look into energy carriers. By definition, an energy carrier is a substance or a phenomenon that contains energy. This energy can then be converted to mechanical work or heat or used to operate chemical or physical processes. We have encountered different types of energy. As we move from one energy form to the another energy form, carriers changes. The most common energy carriers contain chemical energy. Chemical energy is the potential energy stored in the chemical bonds between atoms and molecules. Fossil fuels are a good example of chemical energy stored in coal or natural gas. Chemical energy in fossil fuels is the potential energy stored in the hydrocarbon bonds. Chemical energy is also stored in plant matter, including wood. Gases such as hydrogen and ammonia are also being developed as new energy carriers. The synthesis of these gases stores energy within the chemical bonds of the molecular structure and can be transported as a fuel. If the energy to run these synthesis reactions is supplied by renewable energy sources, we refer to these energy carriers as synthetic fuels. Lastly, the most well-known energy carrier that we will use every day is the food that we eat. It's also chemical energy. Like chemical energy, mechanical energy can also be contained within energy carriers. Mechanical energy is the total energy an object has from its motion, kinetic energy, and position, potential energy. A damped reservoir is the best example where the potential energy of water is contained and can be used to generate hydroelectricity. Mechanical energy can also be stored in pressurized air and recovered by releasing the pressure. In a somewhat similar manner, cold springs store elastic potential energy as well, and flywheels can also store rotational kinetic energy. Electrical energy is perhaps the most commonly used form of energy in our daily lives. A dynamic carrier for electrical energy is electricity itself. Electricity is the flow of electrons or other charged particles through a conducting material. Electricity can be used to produce heat or do work. Electricity has a very high exergy since almost all the energy can be directly used to do work. We will come back to that in this course. Batteries are static electrical energy carriers. The energy is actually stored chemically but released as electricity. Capacitors are electronic components that store electrical energy in an electric field, acting like a tiny, fast recharging battery that releases energy quickly. They consist of two conductive plates separated by an insulating dielectric material, storing charge when a voltage is applied and releasing it later. Crucial for filtering, timing and energy burst in devices from camera to EC units. However, the amount of energy that can be extracted is very small compared to a battery. Thermal energy is more challenging to store owing to the high rate of heat dissipation. Concentrated solar power plants use mirrors and lenses to focus the solar radiation and heat up a liquid. Molten salts are generally used to store latent heat in their solid to liquid phase change and therefore are much more efficient than heat storage in, for instance, water. The heat stored within the Earth is called geothermal energy. It's generated by planetary formation and radioactive decay, warming up underground rocks and fluids. This is known as geothermal energy and can be considered a thermal energy carrier. Finally, steam generated from heating water has been used as the energy carrier to drive pistons of steam engines since the 19th century. Most energy carriers can be traced back to the energy of the sun in one way or another. Solar energy, in a way, is the principal form of energy on Earth. It can be converted into heat and electricity, which are the two major energy carriers used to perform work in our current-day energy systems. Photovoltaic solar panels convert solar energy directly into electricity, while the heat generated by the sun light absorption can also be used directly. Thermal energy can also be used to generate electricity in thermal power plants. Solar energy is stored chemically in plant matter or algae via photosynthetic process. This is called biomass. Biomass can be used to provide both heat and electricity again. Biomass that has been compressed under the Earth's crust for thousands of years is converted into fossil fuels. Fossil fuels can again be used to generate thermal and electrical energy. Solar energy creates temperature difference in the atmosphere and makes the winds move. Solar energy evaporates water and perpetuates the water cycle that gives rise to rain, rivers, and lakes. Both the wind and the water contained in rivers and lakes can be used to generate electricity as well. Most forms of energy that we use are thus derived from the sun, the solar energy. The energy from the sun is converted and stored in different ways on Earth, but how much energy is contained in the different carriers we know? We can express this in terms of the energy per kilogram of fuel stored. For example, gasoline has an energy content of 12.4 kilowatt hours per kilogram of fuel. In comparison to this, another imported fossil fuel, natural gas, has an energy content of approximately 12 kilowatt hours per kilogram, so it's quite similar. When we compare these fossil fuels to, for instance, compressed hydrogen, we can see why there is so much ongoing research in the hydrogen field, as it has a very high energy content of 39.5 kilowatt hours per kilogram, depending, of course, on the pressure. Now you have an idea of the energy content of some of the most important energy carriers. This will help you estimate energy quantities from renewable sources and make you able to compare them. In the energy system, one form of energy is converted into another form of energy. So let's talk for a moment on the energy conversion. I would like to introduce you to my hero, Abdi Nagiye. Abdi won the gold medal in the men's marathon at the 24 New York Marathon and the silver medal at the Tokyo Olympics in 22. In New York, he finished the entire 40+ kilometer run in 2 hours, 7 minutes and 39 seconds. During his winning run, Abdi ended up burning an incredible 3.24 kilowatt hours of chemical energy. This translates to 1.11 human units. This means that Abdi consumed the energy required during an entire normal day in only 2 hours of extreme exercise. Now, marathon runners usually maintain a steady pace for most of their run. Assuming Abdi expended energy at a constant rate, the average power output of Abdi equals to 1.52 kilowatts. That is about 2 horsepowers. As a comparison, the power output of a regular human in rest is about 0.1 kilowatts, 100 watts. Maybe now you understand why most of us, like me, will not be able to match Abdi's power output, certainly not for over 2 hours. Let us use his power performance and call it a Abdi unit. The human body is incredibly efficient at producing power from the chemical energy it receives through food intake. How efficient? Let's first compare Abdi's marathon performance to the energy contained in a Big Mac. How many Big Macs do you think Abdi would need to eat to gain back all the energy that he spent in his marathon run? 1 Big Mac, 5 Big Macs, or 20 Big Macs? He would need the energy equivalent of just 5 Big Macs to make up the energy lost in an Olympic gold medal winning marathon run. This tells you both the incredible power that Abdi was able to produce over 2 hours, as well as the calorie content in a Big Mac. But how does the Abdi power unit compare to the power rating of some common appliances? Consider the energy conversion required to bring a pot of water to a boil. Most cooking stoves use a form of liquefied petroleum gas or LPG to produce fire. When we turn on the gas stove, the chemical energy in the LPG is converted to heat and light energy. The fraction of energy converted to light does not directly contribute to the cooking process. Most of the heat from the flame is transferred to the pot and the water contained in the pot. Some of the heat is also transferred to the surrounding air. This is why it feels warm if you put your hand close to the gas stove. Let us label the energy content of each of these boxes. The chemical energy of the gas used is G, and the energy content of the hot water is W. The dotted line represents the system boundary for our energy conversions. The total energy within this boundary will always remain constant. This is summarized in the first law of thermodynamics, also called the law of conservation of energy. The law states that energy cannot be created or destroyed, but can only be converted from one form to another form. This law is always valid, as long as the system boundary has been correctly chosen. For example, if we were to draw a system boundary around only the LPG and heat blocks, we will find that not all of the energy from the LPG is converted into heat. The law of conservation of energy does not allow this, and it means that we have missed an energy conversion from our calculation. Mathematically, energy conservation means that G, the chemical energy of the gas, is equal to the thermal energy Q plus the energy in the light L. The thermal energy Q is equal to the thermal energy in the air, the pot, and the water, A, P, and W in this example. It also follows that G will always be greater than Q, since a burning flame cannot create heat without light. Similarly, the energy content W of the resulting hot water can never be more than the heat contained in the flame Q, or the energy content of the LPG G. This means that while we have conserved energy in this conversion, the amount of work that can be done by the pot of hot water will always be lower than the amount of work that can be done from using the LPG directly. This is the concept of exergy. The exergy content of an energy carrier is defined as the maximum amount of work that can be extracted from it. Let's return to my hero Abdi. If we assume he weighs 54 kilograms and knowing that he ran the marathon at an average speed of 5.5 meters per second, we can estimate that he needed roughly 380 watts of mechanical power for running itself. In 2 hours he used then 0.81 kilowatt hours of mechanical energy to run the marathon. He burned 3.24 kilowatt hours of energy, meaning that 2.43 kilowatt of energy was lost in other processes. The exergy of Abdi's fuel to run the marathon is 0.81 kilowatt hour. Exergy is an important concept, especially with thermal processes. The energy and the exergy of electricity is almost the same, since electricity can directly be used to do work. We will come back to that in this course. The exergy of a fuel will always be lower than its energy content, since usable energy is always lost in its combustion. Now, let's introduce the concept of efficiency. The efficiency is the ratio of useful energy output to the total energy output. The efficiency of Abdi during the marathon was the mechanical energy delivered divided by the total chemical energy supplied or burned. His conversion efficiency during his run was impressively 25%. We will deal with energy efficiency of energy and conversion and exergy flows of certain processes in more detail when we discuss the energy system. Talking about an energy system, what is an energy system? We will introduce that in the next video lecture. See you in the next video lecture.